Okay, let's start. So, hi, welcome. Good morning to today's first presentation. And I want to share with you some of the experiences that I've acquired by working with AWS Lambda over the last 12 months. And basically, the idea of my presentation is to focus on some of the unique challenges that you'll face if you decide to use AWS Lambda for your next service, or just highlight some of the things some aspects that are less commonly talked about. Because it's very easy on the internet to find information why you should use a given technology, but it's much harder to find information why you shouldn't use it, or what things you will have to fight with if you decide to use it. I hope that after this presentation, you'll be better equipped to make a decision if AWS Lambda is the right fit for your next service. And if you're already using AWS Lambda, maybe you'll pick a thing or two, a technique, an idea that you can apply to your existing service and improve it in some way. First, some technicalities. I need to have a disclaimer, which means that all of the opinions presented here are of my own and not of my employer. Number two, Q&A. You probably know it. Just go to slide.do, use the hashtag GeeCON 2022. You can ask questions there, vote on them, and I'll answer them at the end of the presentation. And the last part, all of the code that I'll be referring to in this presentation, I've put up on my GitHub. It contains the Java code, but also CDK templates, so you can very easily deploy the code in your AWS account, play with it, experiment with it. So yeah, it should be quite easy to work with. A little bit about me. I've been working with JVM for almost a decade. Since the beginning, I've used Java, and since 2015, I've been using Scala on and off, depending on the project. Until February last year, all of the software that I've helped to develop was deployed either on-premise, so in data centers, or on virtual machines like EC2 or other things, but basically on servers. But in February last year, I've joined a team in Amazon that used Lambda extensively across 2 different services. And since last year, I've helped to maintain those 2 services, but I've also co-authored 2 additional services on AWS Lambda. Agenda for today. Number 1, cold starts. I'll talk about what are they, what is their impact on the client latency when calling your Lambda, how JVM makes them even more problematic, and a couple of ideas how you can reduce them to improve the customer experience of your service. Then I plan to discuss the costs or the price of using Lambda and try to answer the question, is Lambda expensive? And compare it to AWS Fargate so that you have an idea maybe when to switch to a different compute platform when the costs start ramping up. And in the last part of the presentation, I'm going to talk about in-memory caching, so something that is very often done to speed up or to improve the latency of our service, and why it's not as easy as it would seem if you want to do it with AWS Lambda. So cold starts. To understand cold starts, what are they? We first need to understand the life cycle of a Lambda function. So when you deploy the code to a Lambda, it doesn't do anything, Lambda does not execute it. Only when the first invocation, when the first request arrives to your Lambda function, the AWS Lambda AWS service creates an instance of your function. That instance goes through a very specific life cycle, which phases you can see on the slide. So initially, Lambda needs to initialize the runtime and your function. So if you're using JVM, it means that it needs to create an instance of the JVM, and then it needs to initialize your code. In practical terms, it means that your handler constructor will be called, and also things like static variables and static initializers will get initialized. So that takes time. And the customer, the caller of your Lambda, they don't care about that, oh, Lambda needs to create an instance. They're just waiting for the response. So that's a cold start, which I've called cold start type 1. This is the standard cold start that when you Google about cold starts in Lambda, that you'll read about. The other type of cold start is unique to JVM, or basically to languages that are not like C++ or Go, where you compile the code and basically a lot of the optimizations are done during that time and so on. JVM does a lot of the things in a lazy way. Specifically, it only loads classes that it really needs. So even if you provide a class path with, I know, like millions of classes, only classes that the code that is executing needs will be loaded. That takes time. Another thing, JVM compiler or Java compiler does not really perform a lot of the optimizations that, for example, C++ compiler does. That means that initially, like couple of initial, like hundreds or thousands, depends on the JIT compiler, the first passes through your code will be much slower than the subsequent ones. So again, your clients will see the effect of that. And this is something I'm calling in this presentation cold start type 2. And just to show you some code, this is an example Lambda function, and basically all of this code will get executed in the function init. So we have a constructor, we have some final variables, we have the static variables being initialized, and we have even a thing called static initializers, the code in the static block, which is maybe not super well-known feature of Java language, but there it is. So basically, all of this code will get executed once per Lambda instance before that instance can actually handle the request. Another important thing is that in Lambda, each instance of your function can only handle one request at a time. So let's take a client which invokes your function, and this is the invoke number 1. Lambda will create the instance of your function, and the lifecycle, like the lifecycle phases will happen. And if the same client or a different client makes another request to your Lambda function while the first request is being processed, another Lambda instance will be created by AWS Lambda to handle that request. And then the responses will arrive to the client. So the effect of cold starts on your clients, on the clients of your service, depend, among other things, in how many concurrent requests your Lambda function will need to handle. Because if you are receiving a steady stream of requests, one request at a time, and the client is so nice to only call it when the previous request has ended, the Lambda will reuse the container. But if you have concurrent requests that need to be handled, Lambda will create multiple containers. And Lambda will try to reuse an existing container that doesn't do anything, but you don't have any guarantees how long it will actually be quote-unquote alive before being recycled. Okay, now let's look at some of the like example timings and try to understand how long are cold starts in case of a JVM. So this is a very simple function. It doesn't do anything, basically. It initializes a logger, like gets some time measurements in the constructor, and in the business logic, the method handle request, it again does some basic things like parsing the input, getting some field from a JSON, doing a very simple computation, like deciding what string to create, if the number is even or odd, logging it and returning. So it's a very simple, like production code is much more complicated. So I've deployed this very simple code to AWS Lambda to a function with 128 megabytes of memory. That part is important because Lambda speed, the speed of your Lambda function, the processor speed, scales with the amount of memory you allocate to a function. So a function with 128 megabytes of memory declared will be quote-unquote slower than the function for which you declare 1 gigabyte of memory. So keep that in mind. But let's look at the timings. The first request that I did to the Lambda, the duration is 85 milliseconds. And this is the duration of our business logic, the handle request time. And like 85 milliseconds, you may think, oh, that's reasonably low. We can live with that. But the init duration is almost 2 seconds. So even if your handler is super fast, the initialization may take a lot longer, like 1 order of magnitude more time. And from a point of view of your client, the request took almost 2 seconds. Then, after like a minute, like 2 minutes, and then a couple of minutes, I did subsequent requests to that Lambda function. You can see that the init duration is not reported, which means that the Lambda decided to reuse the container. And the cold start type 1 doesn't really affect us. And we see the timing, the duration around 2 milliseconds. That's really fast. Yeah. But after around 15 minutes, since the original request, I did another request. And now, again, we see the duration going up, 72 milliseconds. And again, the init duration is reported, which means that Lambda decided to throw away the container that was already warm, quote unquote, and create a new one to handle the request. So there are no guarantees how long the container will be reused. Some places say 15 minutes, some places say 60 minutes, but you can't rely on specific number in your assumptions when using AWS Lambda. Right. Now let's look at the cold start type 2. And let's have an example with a code that is closer to reality. Because when you have your services, when you have your programs, there are multiple branching code paths, and those can be for different types of requests, different types of clients, etc., etc. So in this example, I've expanded the business logic, and based on the input, for one branch, the 1,000 random numbers will be generated, and some math statistics will be calculated using the Apache library. And in the second branch, Jackson library will be used to parse the JSON, map it to our custom class, and call the toString method on it. So we have two distinct code paths that use two different libraries to basically implement the logic. Here, I'm going to ignore the init duration and the type 1 cold start, just to focus on the impact of the JVM on the function performance. So we see the 3 requests to code path 1. The first duration is over 700 milliseconds. That's quite long, depending on who you ask, but subsequent requests are faster. That's because the JVM in the first pass through the code loaded the classes to memory, did maybe some initial optimizations, yeah, those sort of things. So subsequent requests to a specific code path are faster until Lambda recycles the container. Now, I've did a request that ended up in a code path type, second code path. And the duration goes above 1 second because the JVM had to load a different set of classes, because now we are not using Apache, we are using Jackson to parse the JSON, and Jackson wasn't used in that Lambda instance before. And the second thing that the JIT compiler could do is assume, oh, that other code path, it will never get executed. So it made some speculative optimizations that it now needs to roll back. But the second request to a code path 2 is again much faster, 2 milliseconds. And this is not some theoretical example. In one of the services that we maintain in the team, we've noticed that in the tail latency distribution, we've seen the spikes. And when we've investigated, we've noticed that most of the time was spent deserializing the request. which was weird because those requests were quite small. So after adding additional metrics and logging, we've observed that those were basically the first requests of that type coming to our Lambda function. And the clients basically, quote unquote, suffered the cold start type 2. So what we did was, because we were using provision concurrency, which I'll talk about in a second, we basically, in the function initialization phase, we went through all the, invoked all the most common code paths just to preload the classes and have a JVM ready to handle such types of requests. So how can we reduce the cold starts? So one idea is use provision concurrency. And this is, I think AWS usually recommends it as a way to reduce cold starts. And I'll talk about that in a second. But basically, you ask AWS Lambda to keep a number of instances of your function ready to handle the requests, which means that they will be after the init phase already. And when the first request arrives, if the request arrives to them, they will just go to the invoke phase. Again, the other thing you can do is have a background traffic. This is something people did before provision concurrency was present. And the idea is you create a stream of artificial traffic that hits your function. And the idea is that that artificial traffic will keep enough instances up and running and ready to handle the request. It is a best effort attempt, because you may have situations where all the quote-unquote live containers are handling the artificial traffic, and the client traffic will be, the clients will be unlucky, and their requests will be handled by a new instance. So that's not something I would recommend, but I've seen people do that. Third option is that you just use a different runtime. So maybe you decide, cold starts are too much for my service. I need to improve the overall latency, so we can use a language like Go. Or you can use the Graal VM and basically do the ahead-of-time compilation for your code. There are already a couple of blog posts on the internet that describe how you can use Graal with Lambda. I've included a link to one of them here, but just basically type Graal VM Lambda AWS, and you'll find some manuals and instructions. Now, let's take a look at provision concurrency and how we can take advantage of how it works in order to reduce both the cold start type 1 and type 2. So type 1 is reduced out of the box. Lambda will just keep, let's say, 5 instances of your container, of your Lambda function ready to handle the requests, and it will first route the requests to your function to those containers. But the other thing you can do is something I've mentioned, is you can pre-warm the code paths that you'll know that the requests will go through. So this is the code for a constructor of a function where I've added this loop to basically just invoke the business logic with some of the example inputs. And this is basically the same function I've used in the previous example, but with this code added. And let's see the time measurements that we get from invoking it. So we see that already. First request to code path 1 is 33 milliseconds. So, and without the provision concurrency and pre-warming, it was 700 milliseconds. So that's already a significant improvement. The 33 milliseconds is probably because there will still be classes that are not loaded, or the code that was never executed. For example, when the Lambda receives your request, does some things to it initially, but the improvement is significant. The subsequent requests are fast. This is something we would expect. Now, the first request to code path 2. Again, it's at the level of 2 milliseconds. That's because we've already executed the code path 2 and 1 in the function constructor. So that's the JVM already loaded the code and can execute it much faster than in the previous example. Some of the best practices and things to keep in mind when you use provision concurrency. Number one is you need to make sure that your function is invoked through an alias. And what I mean by that is you don't set provision concurrency on a function itself. You set it on a specific version or an alias which works like a pointer to your function. The situation is that the alias has a different ARN or like identifier in AWS infrastructure. So even if you enable provision concurrency, if you don't update your clients and the code through which they call your function, the provision concurrency won't be used. And I've seen it a couple of times where people forgot about this small detail. They enabled the provision concurrency, they paid for it, but it wasn't really used because the function was still being invoked through a name. CloudWatch and out of the box has a very useful metrics for provision concurrency. Spillover invocations will tell you how many requests couldn't be handled by provision concurrency. Then it can give you an idea, should I have more containers? Should I increase the provision concurrency or not? That's up to you. But this is a very useful metric to look out for. The second thing is utilization. So it tells you from 0 to 1, the percentage, quote unquote, how many provision containers are being used. The nice thing is that you can set auto-scaling policies on that. So you can even auto-scale the number of your provision concurrency instances based on the, for example, traffic or the usage. Because maybe your service handles different volume of traffic in a different parts of the day. You don't want to pay for 20 provision concurrency instances, so you can auto-scale that number. 3, this is something we've seen. So pre-warm your function, basically pre-execute the code of your business logic in the function constructor. The nice thing is Lambda tells you if your code executes in a context of provision concurrency or on demand. So you can even make a decision in your code that if it's on demand, I don't really want to pay the upfront cost of preloading the code, and you'll basically spread the effect of cold start type 2 across multiple requests. And the last thing, you can use code deploy with Lambda and code deploy policies to gradually shift the traffic from the old version of the function to the new version of the function while keeping a given number of provision concurrency instances up and running, so that there is no situation where you basically take the all provisioned instances down and then up with the new version, and then there will be a period of time where the provision concurrency can be used to handle the requests. To recap, cold starts can really affect the function latency from a client perspective. And as we've seen, the JVM makes situation even worse. You can accept that, and maybe your service isn't really latency critical. Maybe it's some background process, and that's fine. Or you can use provision concurrency and pay for it. Or you can use the Graal VM and ahead of time compilation. And the last thing is, and this is a general note, you should monitor and instrument your code to understand where are the bottlenecks. Because once you understand where are the bottlenecks, you can make a decision. Do you want to optimize that or not? Now let's talk about the AWS Lambda cost. And I'll show you some examples and compare AWS Lambda to Fargate in some scenarios, just to give you an idea about the baseline price and maybe when it makes sense to use something else. But first, when you use AWS Lambda, you are built, and you don't use provision concurrency. You are built for two things. One is this unit called gigabyte seconds. This is basically the sum the amount of time your function was actually handling the requests times the memory allocated to your function. And AWS has this like table with prices for gigabyte seconds per region. Additionally, you pay for every invocation. It's not a lot, but it can add up if you handle all of the requests. If you use provision concurrency, you pay for keeping the given number of instances ready to handle the requests. Again, you pay for gigabyte seconds. And then you pay a different rate when the instances, the provision concurrency instances, actually handle the requests. Plus, you pay for invocations. The last thing I want to mention about pricing is the free tier. This is a monthly allowance for on-demand instances of Lambda, and for free you have 1 million invocations and 400,000 gigabyte seconds. And those two things are like one does not cancel the other. So even if you use your 1 million invocations, but maybe your function is very it's not really memory hungry, you didn't allocate a lot of the memory to it, you will still not pay for gigabyte seconds up until you use 400,000 gigabyte seconds in a month. So this is something really worth keeping in mind. In order to estimate how much we'll pay for AWS services, there are probably multiple tools that you can use. You can write your Excel spreadsheets. But the nice thing is that AWS offers this tool called Pricing Calculator. And there you can select, oh, I want to use this AWS service, I will handle this amount, this many requests, and so on and so on. So you can create this comprehensive cost estimate for your infrastructure. And the nice thing about Pricing Calculator is that you can share your estimate then, like you'll get a link to it. But you can also see how AWS, how the final price is calculated. So you see the intermediate steps. So you can understand where the cost is coming from for specific services. I included a link to the estimates that I'm going to use in this presentation, so you can take a look at them yourself. And this is a screenshot from the pricing calculator, just to show you that the detailed breakdown, for example, for Lambda, so how much we would pay for compute, how much we would pay for requests, and so on and so on. In order to actually estimate the cost, I need to make some assumptions because I need to make them to calculate things. So I'm going to assume average request time is going to be 200 milliseconds. So in other words, on average, our Lambda will be processing requests in 200 milliseconds. We will look at the monthly costs. That's because the AWS Pricing Calculator reports monthly costs. I'm going to use US East 1 region. Each region has a slightly different pricing, but it shouldn't affect the conclusions that we arrive to when looking at the numbers. And I'm going to focus only on the compute costs because this is a presentation about AWS Lambda. So I'm going to ignore things like egress costs of traffic from AWS and so on. So I'm going to look at 3 different scenarios. Number 1, this is like a hello world function that we've already seen, and just see how much we would pay for on-demand versus provisioned capacity when handling a continuous stream of requests. Then I look at some sample comparison between Lambda and Fargate. Again, this is going to give you some idea how much Fargate costs versus Lambda in a simplest case. And the last scenario is going to be looking at a real live use case. So I'm going to do some back of the envelope calculations, how much it would cost to host the backend for Stack Exchange sites on Lambda or on Fargate. So scenario number 1, again, 200 milliseconds, function with 256 megabytes of RAM, assuming 1 request per second continuously, that gives around 2.5 million requests per month, so slightly like above the free tier. So on demand is like less than $1, so it's super cheap. Provision capacity of 1, it's again quite cheap. And 1 request per second, like if you don't handle live traffic, you are only doing some background work. That's already like probably way too much RPS that you'll be handling. So yeah, like in those cases, Lambda is really cheap, especially if you fit in the free tier allowance. Another scenario. So Fargate. For those of you who don't know, Fargate is an AWS service where you basically deploy containers as tasks, either to your EC2 machines or like some abstracted machines. So it's a more of a server environment compared to AWS Lambda. Here, the function will have 1,769 megabytes of RAM. That's because as I've said, the Lambda compute power, the compute power of your function, scales with the amount of memory. And according to AWS docs, this is the amount of RAM you need to give to your function to have an equivalent of one virtual CPU like speed. And for the Fargate, I'm going to assume one task, one vCPU, 2 gigabytes of RAM. So they should be comparable, more or less. So on demand, $8.8, still pretty cheap. That's quite a big function. Provision capacity, we now see that there is already a bigger difference between on-demand and provision capacity. Fargate for one task costs $36 per month. So one can say, oh, Fargate is more expensive, let's not use that. But we should keep in mind that in case of Fargate, we should think more about in terms of servers. So we deploy a task somewhere, and it can handle probably more than one request per second, given like modern hardware, even virtualized. So you have more things with you can do more things with one Fargate task. On the other hand, the Fargate task will be deployed in one specific AZ. So in case that AZ goes down, the Fargate will need to redeploy your task. Where in Lambda, it should handle those outage scenarios behind the scenes, like your Lambdas will be created in different AZs. So yeah, like both of the cases have their pros and cons. Now to the third scenario. You may not be familiar with the term Stack Exchange, but you are probably familiar with the most popular site on the Stack Exchange network, which is Stack Overflow. And they basically have Q&A sites for a lot of different topics, like mathematics, like Ubuntu, like cooking, and so on. Stack Exchange publishes the traffic, like like basically some information how much traffic they handle each month. So looking at that site, they handle 1.3 billion requests per month. So that translates to roughly 495 requests per second. So that's like already a more interesting number than one request per second. For Fargate, I'm going to assume we are going to use 9 tasks just to have some kind of an AZ redundancy. And then I'm going to assume I want 6 of those tasks to handle all of the traffic. So that translates to 82.5 requests per second per task. And in case of Lambda, I want to think about the extreme scenario where all of the traffic will be handled by provision concurrency containers. Because we know that, because we assume that each request will last on average 200 milliseconds. So each Lambda instance will handle 5 requests per second. So 495 divided by 5 gives us 99 provision concurrency containers that we will need to use. Yeah, so those numbers are much more interesting. One obvious thing is that Fargate is now much cheaper than Lambda. Like for Lambda, you need to pay thousands of dollars, and Fargate, it's like 324. So one conclusion from that is the more traffic your service will handle, the less basically the Lambda will get more pricey, and you should start thinking about maybe you should switch to a different compute platform. Does it make sense to pay for the Lambda abstraction? Is it worth it? The other interesting thing I was surprised by when I've been preparing the presentation is that provision concurrency is actually cheaper. And it turns out that gigabyte seconds of compute are cheaper for provision concurrency than on-demand. But there are cases where the free tier for on-demand Lambdas basically is more important than that price difference. But again, with more traffic, the on-demand Lambda will may get more expensive than provisioned capacity, especially if your Lambda handles a continuous stream of requests. So that's basically like a live service handling traffic for Q&A site, Stack Exchange. And I was just curious to see where is the point where we should start considering using provisioned concurrency versus on demand in terms of pricing. Again, it depends on specific use cases. But for example, when assuming a function with 1 GB of RAM, again, average duration 200 milliseconds, we see that the blue line, which represents on-demand Lambdas, is above in cost with provisioned Lambdas around when we need to handle around 32 requests per second on the x-axis. On the y-axis, you have monthly costs. So, it's an interesting thing to keep in mind. Some tips and tricks, and basically summarizing this section. 1. Remember about free tier. It's 1 million requests. It can be quite a lot, especially if you don't want to create a live service and you just want to do some plumbing, maybe for your development infrastructure. Use AWS Pricing Calculator or some other tool to create cost estimates. Even if they're back of the envelope calculations with some simplifications, you'll at least have some idea how much a given architecture will cost you. As we've seen, with more traffic, Lambda can get really pricey. The other thing is, and this is in one blog post they called it well-known secret, is if you are using on-demand Lambdas, you don't actually pay for init phase. And the init phase has a burst CPU. So if you have some computation that you want to do, and you know that it takes a significant amount of time, you can move it to your function constructor. So yeah, and it will be for free. For consistent workloads, the provision concurrency may be cheaper. Again, you should run the numbers and see how it works out for your use case. And the last point, again, a general point, is that the cost of our infrastructure in dollars, that's not everything. You should also consider other factors like how familiar is your development team with a technology. Maybe you already have everything on Lambda. You have already very good internal support. So it makes sense to pay more for Lambda and then get the cost back in terms of productivity. So again, depends on the use case. And yeah, I just included screenshots of a Twitter conversation and a link to the blog post where I found this information about free init phase for on-demand Lambdas and the burst CPU. So that's quite interesting, things you can find on Twitter. Okay, the last part is going to be about caching. And caching is basically we do some computation, maybe read from a database, maybe actually compute something, and we store it so that we don't need to spend time computing something again. So first, let's look at some abstract service and how the service evolves over time. So we start with a server or a set of servers, EC2 machines or whatever. We have our business logic, we have some data store, and we do reads and writes to that data store. Pretty standard stuff. After that, we want to improve, or we get asked to improve the latency of our service. We notice that, read traffic is 90% of our traffic. Let's do something about that. This is very common. We just use in-memory, we create in-memory cache using Guava or Caffeine. Those are libraries available, and there are more of them, to store the reads from a database. So when the request arrives, we first consult the cache. If there is a result there, if it is, we return it. If not, we go to the database, we read it, we store it in the cache. And keep in mind that this in-memory cache, it's each of our servers will have its own instance of that cache. But then, again, we want to improve the read performance. We notice that, our in-memory cache, it gets thrown out of the window during each deployment or when the process is started, etc. So we decide to create like an L2 or out-of-process cache. We may use something like Redis, Memcache, DBX, DAX when we are using Dynamo. And that basically gives us the advantage of not throwing the contents of the cache out of the window during deployments, so that all the servers can take advantage of the cached values in the L2 cache. And the flow is, if it's in L1 cache, return it. If not, if it's in L2 cache, return it. If not, go to the data store, update the caches. Obviously, it's a simplification, and there are a lot of fine details that you need to think about. But it's a general evolution that I've seen a couple of times with services. So how is it problematic why is it problematic when we are using Lambda? So the in-memory cache is an issue here. One is, as already mentioned, Lambda will recycle your containers. And again, this can happen after 15 minutes, an hour, but that's usually, the time frame is usually much shorter than you have your process running on your server. So there may be not even enough time for your Lambda instances to fill out the cache before it gets thrown out of the window. So probably your cache hit ratio of an in-memory cache will be smaller than you could expect from if you come from a server environment. Two is, sometimes we have an in-memory cache and then we say, okay, now I'll add a background thread pool that will do some cache maintenance, cleanups, refreshes, and so on. Because in Lambda, in the lifecycle, our runtime is frozen in between invocations. So even if you create a thread pool, it won't run when the function is not handling the request, which means that your asynchronous background work may get stopped in the middle, and it may never actually finish successfully. For example, it will be stopped when reading from a socket. And the third reason this is problematic is that you don't have any control over routing in your Lambda. So if you have a server environment, you'll probably have some load balancer, reverse proxy, whatever, and you can create some strategies there. For example, if a server X handled a request for a client A, then for the next 5 minutes or for the duration of this session, try to send that client to the same server, because the server already has some information in memory. In Lambda, you basically don't have any guarantees which instance of your function will handle the requests. So what can we do about it? One, we can rely on out-of-the-process cache, the L2 approach. Adding L1, that's perfectly fine, but you may be disappointed with the results. You can use a different platform, like compute platform like Fargate, if this is something super important for you. Or this is a more, I think, advanced topic in the AWS Lambda world. But there is something called AWS Lambda extension. So I'll talk about it a little more, but basically, it allows you to execute an extra pieces of code on top of your function to do some additional work. As an example, AWS App Config, which is a service where you can store application configuration. So the things like feature toggles and maybe some customization and so on. So not a lot of data, but the data you want to dynamically update and send to your application. The recommended way of integrating with their service in Lambda is to use their Lambda extension. So that's one example of where the extensions are used for caching. So a little bit about extensions. That's basically additional pieces of code. I think you can add up to 10 of them with their own init and invoke phases where you can do extra work. The important thing is that your extension will get invoked on every function invoke, but the code is able to run even after your function returns a result. So this allows you to do this like background work without it being abruptly stopped. And if you want to then use that for caching, you have two options, at least. One is save the cache contents on a Lambda file system, which is shared between the extension and your function. Or two, you can expose a server, HTTP server, on a local host, and basically the extension will be the server, your function will be the client, and function will ask for the cache contents. And the approach number two is used by this AWS AppConfig extension. So, like in terms of the lifecycle, we see that we see the extension phases now. The extension init like happens in between runtime and function init, and the extension invoke starts when the function invoke starts, but it can last longer than the function invoke. It won't get stopped. So what are the advantages and disadvantages of using extensions for caching? One is we can do this kind of asynchronous updates or work, but still keep in mind that they will happen only when your Lambda instance is being invoked. If it's not, then nothing will happen. Two, they introduce overhead, and it depends on your specific function, like how much, how long your function will handle the request. But for a very simple Hello World scenario, I've created a Hello World function that we've already seen, Hello World extension, deployed it, did like 100 requests to that function, and we see that without the extension, the average request time from a client perspective was 1.88 milliseconds. With an extension, it was 14 milliseconds. Again, it may depend on your use case, how significant is that difference, but before deciding on using the extension, you should measure its impact. Even if the extension can execute after the function handles the invocation, the function won't handle any new requests until the extension finishes. So if your extension invoke phase lasts really long, more containers will need to be created by AWS Lambda. And extensions instances are not shared between Lambda instances or containers. So again, there is no way of sharing the cache in-memory cache instances between the instances of the function. So to recap, in-memory caching in Lambda is more tricky because of the container recycle and the lack of asynchronous updates. You can use extensions, but they come with a lot of disadvantages, and they complicate the code quite a bit, in my opinion. So you can use L2 cache, L1 for in a best effort way, or you can use a different compute platform. And that's basically it. So let's look at if there are any questions. Okay, so let's see. So how does provision concurrency look in comparison to EC2 in terms of costs? So I think EC2, again, I think the general rule is that the more traffic you get, the more pricey the Lambda will be. So depending on your traffic, I would just use the costs, the tool from the AWS to estimate your costs, because it may turn out that you need so much provision concurrency that it just makes sense to use EC2 or Fargate. Okay. The second question: are the two types of calls that are occurring next to each other? How they relate to each other? Do they delay stack? So you could say that one occurs after the another, because the type 1 is about the init phase, and the type 2 happens in the invoke phase, and the invoke phase will happen after the init phase. So first the clients will wait for the function to initialize, then the invoke will happen, and then JVM will need to do its thing. And I don't, okay, because there was a second part of the question I didn't really know how to answer. Do they delay the stack? So if you ask this question, you can come to me and we can discuss it. Aren't these solutions simply a workarounds that kind of guide us to the conclusion that we should do something other than Lambda? In my opinion, sort of yes. that was the idea behind my presentation, is that AWS Lambda is not the best fit for all use cases. So you should keep those things in mind when making a decision. And AWS Lambda, it's really nice in the initial days of the development. You can deploy quickly. You don't need to worry about the infrastructure, like updating your hosts, patching them, and so on and so on. But after 6 months, you may discover that now we are dealing with cold starts and the lack of good in-memory caching and other problems, and then you regret choosing AWS Lambda. So yeah, like choosing AWS Lambda may be a significant decision because the migration may be difficult to other platforms depending on your service or product. So yeah, just you shouldn't just choose AWS Lambda like based on just looking at the advantages that people write in the internet. Okay. But Lambda is really nice for like things that are not latency critical. Again, doing plumbing or like responding to events, like, a read happened in S3 and I'm going to do something with it, and I don't care if it's that result is ready after 1 minute or 2 minutes. And there are a lot of use cases like that. Can you give a good example of usage? Yeah, so something that, again, the good fit, I think, in my opinion, is basically those things that you don't care about the latency, that basically process events and you don't have clients waiting for the responses, and they don't want to wait more than like X amount of milliseconds. And maybe like your product, like when choosing Lambda, you already think about, one day I'm going to switch to a different compute platform, but I'm going to use Lambda initially because it's easy to develop. You get a lot of the things for free. And with that mindset, you may first use Lambda and see, maybe this service won't really be popular or whatever. But once it gets popular, like you have a lot of traffic, you start thinking about the migration. But because you've planned for it since the beginning, you didn't. It will be easier for you. Like you won't be surprised, now I need to spend like 2 years migrating to EC2 or Fargate because I didn't think about the limitations of Lambda. So yeah, if that's it, then thank you very much for attending my presentation.